Now we will look at another uninformed search algorithm called depth first search. It's a super simple algorithm. What it does is that it always expands the deepest node in the frontier. However, we still have some starting principle or convention of whether we will start left to right or right to left for the first level of depth. So if you look at the same tree that we traversed through breadth first search first, let's see what is in the frontier and what is explored. At the first level, our frontier is a starting node, also a node. At A, we have only one frontier, B. When we reach B, we'll actually have two frontiers, C and D. Now, depth-wise, at this point, there has to be a convention declared whether we're going to first go left or right, because right now we don't know the depth level of either side, but we have to start from somewhere. Let's say we declare our first choice to be rightmost, sorry, leftmost. So at the leftmost, we reach C, and we have still not reached the leaf node or the end node because C also has a frontier. So at point C, our frontier is the level deeper than C, or the frontier of C, which is E. When we reach E, at D, we have frontier F, but we're going depth wise, and we have still not reached the final most depth of C. So when we reach E and we see that there is no more frontier, we stop there. Now what we have traversed is actually A, B, C, E. We have explored D, but we haven't traversed it because we had not reached the end of the branch of A, B, C, E path, which now we have. Now that we have reached the end of this path, we move to the other side of B, go to D, and reach F. If we try to visualize depth first search in a way that it can be traversed through a maze, which is on the screen, let's see how it goes from A to B. Now this is straightforward because there was only one frontier, again one frontier. Now we have two frontiers, the left side of the maze and the right side of the maze. So we choose the left and keep moving depthwise. Again the same fork, two frontiers, but we are going left first. Now we have reached the leaf. So we come back and we go to the right side. So we have actually traversed the depth of this path as much as it was possible, which means this option and this option. The other choice was going right. So now we go right and depth wise till the end, but we still don't have the goal state. So we come back and look at the other possibility of the depth, which was the right side. Now we will go depth wise to this end. And after not reaching B, we will split into this. Um, Now, depth first search will not always get you the best, shortest path. Sometimes, in touching the depth, if it starts traversing at the more deeper levels, it can actually take longer routes. And if it starts traversing at a shallower level, the chances that it will get the results faster. For instance, in this example, you can see that although there was a shorter path, but depth first search took the longer path. It's not the optimal path that the depth first search guarantees. Now let's look at some of the variants of depth first search. Now depth first search we know is last in first out, or in terms of data structure it's a stacks. Um, what you see as numbers is actually the traversing path of depth first search. So if we start from left to right conventionally, at 1, the starting node, our frontiers will be 2 and 6, but we will not go breadth-wise, we'll go depth-wise. So we'll explore this all the way till the end, then the other branch till the end. Once we have traversed the depth of this branch totally, that is when we move towards the other side and traverse till the end. Now, this is the pseudocode for depth first search. Let L be a list containing the initial state. So we are maintaining the list, and the list has the initial state where we start from. If L is empty, that means you haven't started, so it's returning failure. If we remove the first node from the list, we check if the node is goal. If we have reached the goal, then we stop, right? And we return the path from the initial state of the node. That whichever path took us to the goal, we just stop there and return it. Otherwise, we generate all the successors of the node, which is also the frontier of the node that we are at, and generate nodes to the front of L. So we keep on moving ahead by generating further and further the frontiers until we reach the end and there is no more frontier. So when there's space restriction, or when there are many solutions that exist, it is a good idea to go for DFS. But if we know that we can get caught in infinitely deep paths, uh, and that we also know that the solution exists at a shallow depth, then it's not a good idea to go to depth first search. It is not complete, which means that we can get stuck in loops and never reach the solution. Even if it exists, it is not optimal. I have just shown you the maze example that sometimes there's a shorter solution, but depth first search takes us to longer solutions. Its space complexity is b to d, which is the branching factor and the depth. And time complexity is b to the power d, which means that if depth is very limited, then we're going to run into a very complicated time complexity situation. Now, to reduce the complications of depth first search, there is a variation or modification called depth limited search. Depth limited search is actually it controls us from running into indefinite cycling by reducing the search scope. So we just declared that we will go to, let's say, limit of 3 and not further. So now our depth, no matter how deep this tree is, maybe it is infinitely deep, but when we have declared that we're not going to go any further, then the limit equals to 3. That means that we will start from the starting node, hop to the first level, and then to the second level, and then to the third level, and stop. So if we first prune our tree to 3 levels of depth, and then we start applying depth first search to this. Uh, Depth limited search is not complete, it is not optimal, and its space and time complexity is almost the same as algorithmically it's the same as depth first search. However, what we've improved is that we have reduced the possibility of running into very deep or infinitely deep or cyclic circles. Another interesting and very productive variation of depth first search is iterative deepening search. Now, we don't know where the goal is, and maybe if we say, let's say in our depth limited concept, limit to be 10, that means we will only traverse 10 levels deep. But the solution was at a shallower point, let's say the second level of depth, we still wasted a lot of time. So to handle that, if we think our solution can be at a shallower level of the tree, what we do is we don't define the depth limit. We say increase the depth on every step until you reach the goal. So let's say the goal is 9. First time our depth will be 1. So 1 is not the goal. Now we, in a depth limited search concept, we go 1 level deep. So now our tree is up till here. So we traverse 1, 2, 1, 7, 1, 8, and we still don't find our goal, which is 9. So now our depth limit is increased by 1 more level, and our tree is as deep as this, and our traversing will be 1, 2, 3, 6, 7, 8, 9, and we get our goal. So we are not going any further because we've reached our goal, and this is how we control the issues of depth first search and depth limit search by iterative deepening. This is a very basic code for depth first search in Python. I want you to know one thing. To understand depth first search, you should understand the concept of recursion, because if we apply the concept of recursion to code depth first search, it is super simple. Recursion says that you keep calling the same function again and again until you reach the end goal. Now, if you remember from my explanation, wasn't it exactly what we do in depth first search? We keep exploring the frontiers until we reach the goal. To apply that, we just create a simple graph over here. we create a class of graph and initialize it. Then this is where we're adding edges. So this add edge 01 takes the parameter 01 over here, and onto the list of graph view, at the index u, the v is appended. This is how the graph is created. Now coming to the logic of depth first search. Depth first search starts here. We check if we have visited the node or not. If we have not visited the node, then we call a method dfs v and visited. Visited is a list of all the nodes we have visited. Over here, where we are traversing the depth first search tree, we just first of all flagging that now this node that has been given to us has been visited and printed, creating the path that we're traversing. And then we'll go into the loop where we check that if there is a frontier to the tree branch that we're traversing, and if the frontier has not been explored, which means visited is false for this index, then call the same method again, which is what recursion does. But this time, when you call this method, you actually call it not on the node that we started, but on the node that we're traversing right now if it is false. So we are maintaining a visited list, and we are going in this loop. I is incrementing, which means we're going level and level and level deeper on this v, and this is how we do it.